I'm Sören Domrös from Kieler University. And yeah, first we talk about the Eclipse layout kernel. I'm currently the project lead of the Eclipse project for the Eclipse layout kernel. So let's dive into it. First of all, what is the Eclipse layout kernel? It's not a rendering framework, but focus only on the computational part of positions. So we have layout algorithms that basically just calculate positions for boxes and lines and where they should go. And we have a little bit of infrastructure just for us. And of course, there are several libraries, but what Nordics ELK, so yeah, often used in many projects is that it has support for ports, which are especially important in the model-driven engineering domain. I at least know of various cases, and hierarchical nodes so that you can structure your diagrams better. Also, there is not only ELK, that's the Java library, but we have a JavaScript library, ArcJS, that we transpile through, which is also heavily used. So these are the weekly downloads of ArcJS, which seem to be rising at the moment, because it's integrated in many different tools. Some of these tools are here, so we actually don't know all of them because it's not everyone writes us when they use our libraries, and sometimes we know because we work with them. Sometimes we know because they make issues for specific things, and sometimes we know because they consume ArcJS and NPM can track which libraries depend on that. So for example, we have Eclipse for DIRC, which is program for distributed industrial process management. Eclipse Sirius, which also just does graphical modeling for various kinds of things. Eclipse Sprotty, which is already, I think, mentioned in some of the previous talks. I think also the bigger tool below here also is based on Sprotty, and GLSP also heavily uses the Sprotty for layout, and Sprotty integrates ArcJS. Papyrus, also a tool for model-driven engineering for, I think, UML diagrams. Also does layouts based on ELK. PlantUML, I think it's fairly new, also has an option to use ELK layout. And the list just goes on. So sometimes we have this kind of layout frameworks that just try to add new kind of layout algorithms as we do ourselves. And sometimes we have tools that directly depend on it. For example, the e-handbook of ITAS Bosch or something like this. What kind of algorithms does ELK have? So we have our flagship algorithm that's ELK layered with kind of these left to right or top to bottom kind of drawings with a clear direction. We can, of course, also pack nodes or rectangles somehow, and we have the normal layout algorithms like force layout, radial layout, tree layout, or some bridges to other algorithms such as libavoid. Below you can see the full list of algorithms if you want to dive into that. But we only will focus on the ELK layered in this talk, and just showcase a little bit of that. But if you have questions regarding the other algorithms, I can also show you examples for this. Okay, ELK layout is mainly used. So here you see some of the features. So in a few minutes, we will dive into the actual implementation, how stuff work in there. So this is the overview, how many things work. So we see we have hierarchy, which is fairly important here. We have hierarchical nodes, so we can actually route the edges through them. And we have this explicit ports, and as you see, they might have free assignment to just optimize the layout. For example, here, these might be interchangeable to avoid crossings. And here, as it is the case, for example, for hardware layouts, these ports on specific actors or components in there might also have a fixed order or a fixed side, which is important. Other important features are like the whole variety of spacing and padding. So everything you see supports these, which is fairly important if you actually want to build non-trivial drawings, that you can change this depending on the layout. So usually ELK only supports rectangular nodes, but if you have more special kind of nodes, you might want to have different spacings, different paddings around them to accommodate for that, and also change the position of ports and the like. Here you see the spacing between different components. So we have spacing between different vertical layers here. So for example, here the two nodes 1 and 2 have a position defined by the spacing between them, between different vertical layers. And we also have a spacing between different nodes on the other horizontal spacing here. Maybe change around. This is horizontal spacing. This is vertical spacing, of course, inside these kind of layer and between layers. This, of course, also works for edges and also for ports, which you somehow see in here. So we can just do anything you wanted to do. On the right, kind of visualized how the padding works. So here we have a padding around text labels. We have a padding around inner components here, and also in dark gray around the actual stuff that's happening. We have different port sides that we can then assign to constrain the layout, and also different kind of port distributions depending on whether they want them at the beginning or end of the side, centered, or just distributed evenly in different configurations. Next thing is the node size and the port size, and also the label size might interact. So here on the left, you see that the size of the node is determined by the label inside, plus a little bit of padding around it. And here for N21, you see that the ports actually have a higher spacing between them, which is disregarded to just fit it into the height of the node. And here for N22, we actually let the port spacing define the height, which is also sometimes desirable and can just create anything you'd like. Here we have, again, hierarchical nodes, which can also support hyper edges in a sense, and of course, different kind of port sizes. Port starting point to this port here, P3, actually belongs to the node N3, and usually, if you have like a normal kind of diagram, usually place it here on the border, but you can, of course, just offset it as you like. Next thing that might be important is what we call model order. Sometimes models have some kind of inherent ordering, given if you have a textual model by the textual order, or just by creation order, or some kind of naming that you want to have. For example, the drawing on the left somehow disregards that, because we have here the node N2, the node N3. It could be in a ordered as one want to have it, or here again we have different kind of configurations depending on whether the order of the edges or the order of the nodes is more important. So you can somehow configure that to get drawings that are not only built automatically, but also are similar to what a real person would do, which would not somehow change 2 and 3 around. Same goes here for a different part of the algorithm. So here we're talking about ordering in one of these kind of vertical segments. They're called layers, but we can also do this for the direction of edges. So here we have a problem that just looking at the structure, we don't really see whether the node 3 or node 2 should be before or after one another. If we just consider the ordering that we here is given by the naming, then this decision is clear. So we can just create better reading direction by that. And with that, I would like to already go to the demonstration. So let me change to this, correct? So I will showcase the interactive demonstrator of ELK. So you can also do that if you copy the URL. Maybe I'm quickly doing that and copying in the chat if you also want to try out something. And I'm choosing here the ALCT model currently. But first of all, let's look at examples. So we're looking at this. We have various kind of examples, and I just want to showcase what I meant here by spacing. So maybe you remember this drawing from before, and we can just change any spacing here. So I can change this, and this just changes the spacing not only because of the value, but because of other factors such as how straight lines should be. So here we have the spacing, and now the position of this node 3 is determined by the spacing between this node and the edge, the spacing between the edge and the spacing between the edge and the node 5, that we still have a straight edge here. So if you make that smaller, it might not change, it does not change the position. But if we then again change spacing between edges here to a smaller value, then of course this also changes. What you can also do here is we have a look at the model order. So here you see somehow someone ordered these, which is quite interesting because it happens a lot, somehow ordered these nodes for presentation purpose differently, because somehow the normal layout does not change it. But if we actually consider the not do it correctly, the model order, and maybe say we prefer the edges here, and then create the correct ordering of the nodes here, and just move it here, and now consider the order of the edges below here, and move the edge from N2 to N5 below here. We see that this is the same drawing as before, and this can help us just have better orderings without considering here we use this semi-interactive with different position constraints in here, which also work, but it's more tedious to implement. And if you just want to do create a model, you can just use the ordering that you already have for this. Next up, we will have a look at more of the different strategies that we might want to use. So I have this. This is the initial model that you might also saw earlier. We have a look at the different strategies for different phases of the layered algorithm. So generally, we have 5 phases because it's kind of Sugiyama type of layout. The content assist does not work in here, sadly. Currently, where we just change how this is laid out. So for example, we could do depth first, which somehow changes how this might change the direction of edges, or consider the model order in different kinds of ways. If you see if this ordering is actually not intentional but somehow random, this is stupid to just consider the textual ordering. So the default is something like this, where we, or this, where we just use it as a tiebreaker somehow. The layering is also important, so we can set a layering strategy, which also might optimize different things for minimum width or different strategies. So just a collection of a whole lot of things. Crossing minimization strategy, which might be this is the ordering inside these kind of layers. Or content assist is broken again, which then just does this kind of layer sweeps. Or node placement strategies. Strategy, which might change the kind of alignment that we create here, whether the edges are more straight or not. And depending on the straightness, we also have different kinds of ideas how straightness should work. So this is a balanced kind of solution, but we could also center, do it right down. So this kind of secondary edges just go below somewhere. Here you also see these layout constraints. So each node might have port constraints and specify how they might change. And some nodes like this counter below, maybe I can quickly show it. Counter Q1 has this fixed ordering constraint, which results in the order that the ports are just like this, which I can also change to 3 if I'm somehow annoyed by this. Which here makes this drawing actually more not more symmetrical, but now you see that these are exactly the same components in here, which might also be desired. So 3 is usually the solution you want to choose if the language itself you're modeling does not constrain the ports somehow. So if you have, as I said, hardware layouts, or for example pipe layout like physical pipes, then you might want to change this. And with that, I think I'm going back to the presentation, which I have somewhere here. Where can you try out Elk? So just use the site I just showed you. You can consume it via Maven Central or as via NPM. And finds a lot of documentation online. Maybe if you have questions further, I also show you what kind of documentation there is for all the different kind of options that you might have. And again, you could contact me like this. And with that, I will try. I think the time for the first presentation should be up, and I'm trying to start the new one. And okay. About interactive diagrams using Kieler. And here the idea will be that we somehow now use automatic layout in different configurations and also have this kind of IDE support for everything. Okay. First of all, we are always using the concept of pragmatics or modeling pragmatics in our layout, in our tools. So we usually have a textual model, which is automatically synthesized in a diagram somehow, which just gives us the best of both worlds. So we can edit textually, what helps if you have like people that coming from programming, just program their stuff. It's easier for version management than just text or just diagrams, because then you have the problem of moving just something, a few pixels, if you have these kind of, you see is what you get editors, and have to somehow save this, and this might change. It's a problem for version management. If someone edits a component and someone moves the component, where's the change in there? So we're usually doing these kind of setup. How does this work? For us, we always start with a model at the beginning. For us, this is mostly a Java model if we're working, because we're somehow familiar with it in the Java world, which is then automatically synthesized. So maybe have like an AST or some kind of description of this in a view model, which actually has some kind of information how elements look like. So for example, if you have a state, the view model would be the model. There's somehow a state, and the view model would be it's a rounded rectangle that's colored in red with a line thickness of 5 or something like this. And also we are doing micro layout for this. This would be the corresponding publication for this. And micro layout would be like all this text placement and relative placement based on this kind of forms that we have in there, which are not really part of ARC. So this actually calls ARC. So because we only have a view model, we want to kind of create different kind of layouts. We need positions for them. So in there, we only get we have rectangles, we have lines between them, and we want positions for them. That's what ARC does. And now we have two paths. We have our legacy path somehow. So previously it was an Eclipse application that we mainly developed. So we also use Glide and Piccolo to render it, to create an Eclipse view from that. And we have like the thing we mostly do now. So we built a language server for that can be shown just rendered in SVG with Proti, or do this in VS Code. So we either can do that, like standalone or embedded in an IDE. And usually we use Xtext or Langrium for create this kind of model to create a language server. So with Xtext, it would be a Java language server, and with Langrium, we are usually in TypeScript. This would be how we would apply that to our Kieler C# tool. So we have a language server that can compile, and we have an Eclipse and a VS Code extension just work with this, and it just uses the same code base. And we also do that for other languages, but I think for timing issues, I'm later focusing more on demonstration, just show a different aspect. So what can Kieler C# do? Again, we have text, we create diagrams, and here we have all the stuff that you might need for this. So we have this filtering, we have different kind of views for this, which can be automatically changed. So the same text might create like its kind of overview or control flow kind of layout, but you can also change it to have a view at the data flow between different parallel components. And this is kind of helpful also for simulation purposes. We again use Glide to style our diagram during simulation. So if you want to know what's actually executed, we can style it. We can have visualizations running for this to just show how it's kind of, now it's an elevator, how this works, which is also interactive, which I might have time to showcase later. Other tools such as Pasta basically use the same concept. Here also we have a model. Here it's generated by Langrium and not Xtext. And again, we use ALG, or here ALG-S, because it's a TypeScript, to create our diagram. And here we only support the Visual Studio Code extension for this, which would then somehow look like this. So we're looking at that now in the live demonstration. So I'm quickly changing tabs. So this here is our C# model that I somehow showed earlier, and I have various kind of interaction with this. So this supports also various layout properties in here, which might change. For example, I can disable or enable any kind of additional information I might need if I want to have labels or comments, which are now here. If you have a look at this, it's a comment. I can look at declarations. So usually they are not interested. I can also look them up in the text, but sometimes you also want them in the diagram, which I can enable or disable, or different kind of state actions that are called, which I now disable, just show what this kind of focus and context approach means. We can also do label management. Maybe I just quickly enlarge this here. So here I just showed everything that is on an edge, but I might just only show the execution priorities to just know what is happening. I can expand or collapse certain parts if I just want to know how this kind of acceleration works for a car or for a motor here. I can just look at this, and this is a very concise view on everything. And also if I do this, you may remember this kind of drawing from earlier. And of course, and I can also look at the data flow between it. So I think now I disabled the labels. Because I disabled the labels, right. So I can also look at the labels again, and here just look how the data flow evolved between the different kind of regions that I have here and how everything is connected. Okay. Next up, we will have a look at the different kind of extension for SDPA extension. So this is language as a system theoretical process analysis. So usually you define this kind of hazards and losses in here, which create these kind of diagrams that also lay out with ALG, which you might also move around a little bit, but this is kind of a spotty approach of this. also what's important here is because all are somehow, it's very lengthy and it's hard to navigate this kind of model. You have, of course, have this kind of interaction between diagram and text, that you click on something and it's highlighted, and also if I click on the diagram, it highlights the connections to other approaches, which also works for this approach. So if I click here and this is open, I'm also highlighting the specific here set speeds diagram. That would work. I'm getting mails. Maybe I'm closing that again. So this works in both approaches. These, for example, can also be compiled. So we also do a little bit of compiler chains in here. So simulated. So if I maybe want to compile a C code and maybe disable the data flow view, open this up. Maybe not that one. I quickly restart that again. No. Then we have our kind of highlighting here, and if I run it, it might also and actually change values to something. You should see that something is happening in here, which kind of transitions are taken. So you may see here, this is already running all the time and just doing the motor stuff, which might be interesting. Okay, to wrap this up, changing back to the presentation. If you interested in this, you of course can again contact me, and I try to get familiar with the technology. You might want to look into Kieler. We also have everything what I just showed in the Visual Studio Code is available as a Visual Studio Code extension. I can also quickly show that again. So if you just search for Kieler, then you find all our extensions. So we have a general extension for diagrams. We have our just like a C-sharps, Kieler C-sharps extension, and some more. This is a SDPA extension. And if you're interested in that, you may know lingua franca for model-driven engineering, which also uses our extensions, which you might also use for this. Yes, so this would be the presentation from my side, and I hope that you might bring any questions for specific parts I should talk more in detail about. Thank you.